Alrighty, guys. So we're finally reached the point where I hope you feel very familiar with parametrics, or at least comfortable enough to deal with them. So now we're gonna bring in calculus and see what we can do with it. Okay. So the first thing I want to talk about regarding parametric equations and calculus is pretty much our second topic that we talked about this class after limits, which is the idea of a derivative. So let's talk about derivatives in parametric mode. So I want you to think this through. We know that a derivative is dy over dx. Agreed? The problem that we find ourselves with is that when we're in parametric mode, you have equations that are, for example, x equals some function in terms of t, and y equals to some function in terms of t as well. Sorry, I wrote y there. So if we're trying to find the derivative in terms of x, we have a problem there because this is not in terms of x. This is in terms of t, and this will be in terms of t as well. So if you think this through, let's say we wanted to find the derivative of this, so that would be dx over dt, right? Makes sense? Which means that then this would be dy over dt. Both of them have this t, this change in t, which we don't want, right? We want to be able to have dy over dx. But what I do notice from both of this is the fact that this one has the dx and this one has the dy. So what if we do the following? What if we do y prime over this x prime and see what happens? So if we take this y prime is dy over dt, and then this x prime is dx over dt. We have a fraction divided by a fraction. So we're going to keep the fraction on the top, we're going to switch to multiplication, and we're going to multiply by the reciprocal. And you should be very happy because look what happens here. The dt's go away, leaving you with dy over dx, which is what we want. So now let's just kind of put this into words and make it official. So let's put a definition. So let's say if a smooth curve is given by x equals f of t and y equals g of t, then I'm going to throw some vocabulary your way. Then the slope at x comma y is given by the following. Why the slope? Well, you got to remember from the first semester when we talked about one of the representations of the derivative is that the derivative is the slope at any point of a function, right? So basically it's another word for derivative here. So the slope at some point is given by, well, we just kind of did a small little proof, dy over dx, so the derivative or the slope is equal to the derivative of the y function in terms of t divided by the derivative of the x function in terms of t. Once again, just a little refresher, if you take them and divide them by each other, they end up canceling out that parameter there, the dt, leaving you with dy over dx, which is what we wanted to. Okay? Awesome. So as you can see, it's not that terrible to find derivatives in parametric mode. So let's go ahead and try an example. Example number 1. Let's say that you have the following. We're going to find the derivative. And I got to give you a set of parametric equations. So let's say that x is equal to sine of t and y is equal to cosine of t. And we want to find the derivative. So the derivative of this thing is dy over dx, and if I go back up here, I need the derivative of the y function in terms of t. So I'm going to go here. The derivative of cosine in terms of t would be negative sine t. So that's going to be negative sine t. And I've got to put that over the derivative of the x function in terms of t. So the derivative of sine t is going to be positive cosine t. Therefore, if I have negative sine t over cosine t, that should reduce or simplify, I'm sorry, to be negative tangent of t. So the derivative in terms of x of this set of parametric equations is negative tangent of t. Okay, so it's really not that bad. So I don't want to do a whole bunch of examples. I would much rather you try it on your own on the homework. I could ask you several things about the derivative, like I could ask you to find the tangent line. I could ask you to find where a tangent line is vertical, where would it be horizontal, and whatnot. But this is not something that you need me to teach you. If you need help, you need to refer back to our video from the first semester about tangent lines and derivatives. Okay? So we're going to go ahead and move on. And if you're able to find the first derivative, then I don't see why we couldn't find a second derivative or a third or a fourth and whatnot. So let's talk about higher order derivatives. Okay, so let's talk about the second derivative. So if you remember notation, let's talk about a derivative. So the second derivative of y in terms of x. Well, think about it. Isn't that taking the derivative of the derivative? So we're going to take the derivative of a derivative. Well, now, remember, we are in parametric mode, right? So we're going to take the derivative, and we found out that the derivative, right, our notation for a derivative is dy over dx, right? So we're going to take the derivative of a derivative, and we knew that the derivative was dy over dx, right? Now, here's the problem that we have and we face one more time. This dy over dx is in terms of t. So kind of like if I refer you back to our previous example, notice how we found the derivative, but it still has a t in it. Well, that's the problem, right? So because we're trying to find this second derivative in terms of x, we need to figure out a way to make that happen, just like we did with the first derivative. So what if we do the following? What if we go ahead and take and rewrite this as, it needs to be the derivative in terms of t, right? Because this thing is in terms of t right now. So this derivative is in terms of t. Well, to balance things out a little bit, I need this was originally the derivative in terms of x, right? So I kind of just changed that. And I can't just change that randomly. So what I'm going to do is, I need to find something that I could multiply this by that would really just bring us back to that. And what if I do this? Because think about it. This dt cancels out, leaving you with the derivative with respect to x, which is what we had. So really what I've done here is I've manipulated what I have here to introduce this dt, because it is with respect to t, but I haven't changed anything. Okay, so what I'm going to do is I'm actually going to clean it up a little bit for you so that you can use what's the official formula that's typically given. Well, we can take the derivative of this in terms of t, so the derivative in terms of t of dy over dx, and multiply them by this fraction. I could actually maybe just rewrite it as divided by that, the reciprocal of it, which if you look at it is dx over dt. So let me kind of summarize to you what this means. This is the official formula, by the way, that you're going to have to use to find the second derivative. So what happens is you're going to have some derivative, right? You found the first derivative, and now you want to take the second derivative. So to do so, you're going to take the derivative of your derivative. Okay? But after you find that, you have to divide it by the derivative of x with respect to t, which if you think about it, that was going back to very, very, very beginning. So that would be like if we were going to try this example, we would have to first find the derivative of this and then divide by the derivative of x with respect to t, which was cosine of t. And we'll try an example here in just a second. Okay? Now, could you find a higher order derivative? Like, could we find the third derivative? Absolutely. So let's say that we want to find the third derivative with respect to x. Well, it's kind of like the same idea. Now you got to take the derivative of the derivative, so that means we got to take the derivative of the second derivative. And really it comes down to the same idea here. We can rewrite it as, once again, this is going to be with respect to t, so the derivative with respect to t of the second derivative times dt over dx, so that it's, again, it's like multiplying by a form of 1. I haven't changed anything, and therefore if we clean it up, we can say that the third derivative would be equal to the derivative with respect to t of the second derivative divided by the derivative of x with respect to t. And as you can see, it's literally the same thing. So regardless of whether it's the first, second, third, fourth, fifth derivative, higher order derivatives, it's always going to have the same form. It just depends. Just make sure that you maintain in order. Okay? So let's try an example. And let's try an example that it's not just finding a derivative. Let's do a little bit more with it. Okay? So let's do example number 2. And let's say that I'm asking you to find a slope. So find the slope, and if we think about it, we're finding a slope, that's the first derivative. But also I want you to find the concavity for the following function. Okay, so I'm going to give you a set of parametric equations. X equals to the square root of t, and y equals to 1/4 t squared minus 1, where t has to be greater than or equal to 0. And since we're finding a slope and a concavity, you need a point. So we're going to say at the point 2, 3. Now, make sure we understand that this is x, y. So we'll talk about that here in just a second. Alright, so let's take this problem step by step. First thing I want to do is I'm going to find the slope. So to find the slope, I need the first derivative. So here we go. We got to find the first derivative. So dy over dx. So remember, to find the first derivative is the derivative of the y function with respect to t. So that will be 2 times 1/4, which is 1/2, t, over the derivative of the x function with respect to t. So that's the same thing as t to the 1/2, so that's what? 1/2 t to the negative 1/2, which looks wonderful to me. These 1/2s are going to cancel out. The fact that you have a negative power here means that it really has to go to the top. So that means I have t times t to the 1/2, so that's going to be t to the 3/2, which means then that our derivative with respect to x is equal to t to the 3/2, which is what's going to give us our slope. Now, when we're not in parametric mode, all we had to do was plug in x or y into our equation. But as you can see, we don't have an x or a y to plug in. We have t. So we need to figure out what that t is. So what we're going to do is we're going to use the knowledge of this point and our knowledge of this functions to figure out t. So all I'm going to do is I'm going to plug in this 2 here for x. So I'm going to say 2 is equal to the root of t and solve for t. So I'm going to say 4 is equal to t. So at this point then, once I have this t value at x equals 2, now I can go and evaluate it. So I can say dy dx evaluated at t equals 4 is equal to 4 to the 3/2 power, which is the same thing as saying 4 times the square root of 4, which is 8. Therefore, the slope is equal to 8 at the point 2, 3. And that wasn't that terrible, and I actually want to add something to this. So let's say not only did I ask you for the slope, but now I asked you for the actual tangent line at that point. Just a refresher, well, now you have the slope and you have a point, so we can write it as y minus 3 is equal to 8 times x minus 2. And that would be our tangent line at the point 2, 3. Now, do you need to clean it up? Not necessarily. So for the AP exam, if you're not asked to clean it up or if you're not asked for a specific type of form, then I would not waste my time and leave it like that. If you do want to go ahead and do so, make sure that you do so carefully. You don't want to mess up on the algebra and then accidentally get it incorrect, even though you did everything correctly, to be honest. It's just one little simple algebra mistake. So to avoid it and to save time, I would just leave it like that unless indicated to change it to slope-intercept form. Cool? Alright, so that takes care of the first part. Now the second part, it says that we need to find the concavity. Alright, so if I kind of refresh your memory a little bit, concavity, you need to find the second derivative so that we can do the second derivative test, right? Now, I'm not really going to have to perform the second derivative test here because they're asking me for the concavity at one point, not over the entire domain. So really what I'm going to have to do is just find the second derivative and plug in the value of 4. Once again, I hope you understand where I got the 4 from, to figure out whether it's positive or it's negative. Because if it's positive, that means that at this point, we're going to be concave up. But if the result is negative, at that point, we're going to be concave down. So now that you know my plan, why don't you go ahead and pause this video, attempt to find the second derivative on your own, and try to see if you can figure out the concavity. Okay? Alright, I'm assuming you already gave it a go, so let's kind of go over it. So we obtained from our last part, or part A, that the derivative of y with respect to x was equal to t to the 3/2. Alright, so to find the concavity, we said we were going to have to find the second derivative of y with respect to x. And if I remember this correctly, I have to take the derivative with respect to t of this thing here. So that's going to be 3/2 t to the 1/2, and divided by, remember the formula, so the formula says the derivative with respect to t of dy over dx, all divided by dx over dt. Well, think about it, that you already have. Let me kind of flip the page. We had it back here on our first part. We found out earlier here that dx over dt was 1/2 t to the negative 1/2. So we already have it. There's no reason for you to find it. So 1/2 t to the negative 1/2. Cool? So now just some simple algebra. These 2's are going to cancel, so that gives you a 3. Now this t once again is going to go to the top. So that's t to the 1/2 times t to the 1/2, which is just t. Therefore, it's safe for us to say that the second derivative of y with respect to x is equal to 3t. So we have our second derivative. We want to figure out whether this thing is concave up or concave down at the given point. Now, because of part A, we already know that at 2, 3, t equals 4. Therefore, I can say, okay, the second derivative with respect to x evaluated at t equals 4 is the same thing as 3 times 4, which is 12. Notice, this is positive. So therefore, according to the second derivative test, since 12 is greater than 0, then the graph is concave up at the point 2, 3. Cool? If you're watching this for the first time and you're wondering, like, what is the second derivative test? Like, what is he talking about? Then I need you to go back and watch my video about the first and the second derivative test. By this point in calculus, you should have already learned all this tests. So that's the reason why I'm kind of throwing this terminology out there. I'm assuming that you already know these terms. So now we're just really just going over calculus, but in a completely different mode. Now we're just doing things in the parametric mode. Okay? Alright, fantastic. So let's try out an example now where I'm going to ask you to find the tangent line, and I'm going to deviate a little bit. So as you notice on my previous video, if you watched it, the one that I asked you to watch before this class, was that the parameter doesn't always have to be t. The parameter could actually be an angle. So let's try something with an angle. So let's talk about tangent lines. And let's say that I'm going to ask you to find a tangent line. Once again, this is not a new concept for you. This is something that you already know. So we want to find the equation of the tangent line at the point 0, 2, given the following equation. X equals to 2t minus pi sine of t, and y equals to 2 minus pi cosine of t. Okay, so we got to find a tangent line or lines of this curve at that point. Alright, first thing first, we need to figure out the slope, which means if we need a slope, we need the first derivative. So let's figure out what that is. So dy over dx, just a refresher, is dy over dt over dx over dt. So let's figure out, here's our y equation. What's the derivative of this y equation with respect to t? Well, the derivative of 2 is gone. The derivative of negative pi cosine t is going to be positive, because it's going to be the derivative, remember, of cosine is negative, so negative with negative makes it positive, so it's going to be pi sine of t. And now we just got to put that over the derivative of x with respect to t. Well, the derivative of x with respect to t, the derivative of 2t is 2. The derivative of negative pi sine t is going to be negative pi cosine t. Okay. So now our job is to figure out the tangent line at this point. Once again, it should be very obvious that this is x comma y, and there's not a place for you to plug in x and y. What we need to figure out is t, or theta. I use t here, but it really could just be theta. Okay? So what I'm going to do then is I need to use these values to help me figure out what t is. Now I'm looking at each one, and I think I'm going to decide to use the y value, because if I use the x value, it's going to get a little tougher to solve by hand because I have a t here. Alright? So I'm going to have to get a little bit more creative. As opposed to this one, if I just set 2 into y there, I'm going to be able to isolate cosine by itself. So let's go ahead and try this 2 in here. So I'm going to say 2 is equal to 2 minus pi cosine t. Alright, so if I subtract 2, that's 0. If I divide by negative pi, that's 0. So that means 0 is equal to cosine of t. Well, you just really need to ask yourself, where in the unit circle is cosine equal to 0? And the answer to that would be, if we take the inverse of this, really it's going to happen at two places. Cosine is 0 at pi over 2 and at 3 pi over 2. So the fact that I got two different t values tells me the following. I'm going to have two tangent lines here. Okay? Later on, I'm going to graph it just for you to check to make sure that you understand why we're having two lines tangent at one point. And we've never really kind of had that before. But we'll talk about that here in just a second. So let's go ahead and figure out the slopes at this point. So first we're going to say dy over dx evaluated at t equals pi over 2 is equal to, alright, so I'm going to do this mentally. So we have pi times, alright, if we plug in pi over 2 into sine of pi over 2 is 1, fantastic. If we plug in pi over 2 into cosine of pi over 2 is 0, so that's 2. So that means that the slope is pi over 2 when t is equal to pi over 2. And when t is equal to 3 pi over 2, we have pi times, well, the sine of 3 pi over 2 is actually negative 1. The cosine of 3 pi over 2 is still 0, so we're still over 2, but this time is going to be negative pi over 2. Notice how it's technically the same slope, but one of them is negative. Okay? So let's answer the actual question. The question was, what is the tangent line? So we have two different tangent lines. We have a tangent line with this as a slope and this as the point, right? 0, 2. So if you remember, that would be y minus the y value, 2, is equal to pi over 2. X minus 0 is just x, so we're going to leave it like that. And we also have the equation y minus 2 equals to negative pi over 2x. And that right there would be the answer for what is the tangent line of this equation, set of parametric equations at this point. So why are we getting 2? Let's kind of talk about and see what this looks like. So for that, I'm going to use a calculator just so that we're not spending time graphing it by hand. So I'm going to go ahead and go into y equals, and actually I need to go into mode. And I'm going to switch this to parametric. And I'm going to make sure that I am in radian. So I'm going to go back into y equals. So there's our x equation. So our x equation is 2t minus pi sine t, if I'm not mistaken. Cool. And our y equation is 2 minus pi cosine t. And we're going to go ahead and hit graph. And actually I need to kind of zoom out. Let's do a standard window. Now, notice how this thing looks like that, and I'm just like, wait a second. So, the graph, if I zoom in, let me zoom in. Oh, sorry, I zoomed out by mistake. My apologies. Zoom, let's try zoom decimal here. The 0.02 is here. So, if you really think this through, these lines are really telling you that your intercept is at 2, which is here. So, it's like you have a line here, but the other one is going in the opposite direction, so how can that be possible? Well, what's happening here is like your calculator, if I go to window, it's starting your time at 0. So therefore, what if we change that up a little bit? What if we go back and don't start at 0? I don't know, let's say, I'm looking at this, as you can see, this is 2 pi. So what if I say negative 2 pi? And I hit graph. And would you look at that? It looks like, I don't know, kind of like a drop here. So what's happening then is one of the lines, this is the point specifically that we're talking about, and I'm okay writing with my calculator. One of the tangent lines is going on that direction there. And as you can see, you're only touching at one point. That's the one with the positive pi over 2. And the one with the negative pi over 2, it's going to be here, which also meets the requirements of a tangent line, which is literally just touching at one point. So really, what I'm trying to show you by this example is that it is possible, now that you're in parametric mode, that you can have multiple tangent lines at the exact same point. Okay? Alright, we're almost to the end of our video, guys. That's exciting. We're going to talk about arc length here in just a second, so let me go ahead and pause the video. I need to get a drink of water. Alrighty, so our last topic that we're going to talk about for this section is the concept of arc length. Now, we literally just covered arc length no more than a month ago, so I'm hoping this is still pretty fresh in your minds. But just in case it is not, let's go ahead and recall that arc length is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. Now, if you're really interested in knowing where that came from, make sure that you watch my video regarding arc length, where I do the derivation of this formula. Okay? Alright, well, we have a problem. Well, this is when we have a function in terms of x, right? And as you can see, today we're talking about parametric equations, which are functions. We have a set of functions that are with respect to t. So we need to make this happen. Really, what's happening here is, you got to remember, I can rewrite this as the integral from a to b of the square root of 1 plus dy over dx squared. Now, if you remember, dy over dx in parametric mode is going to be equal to dy over dt over dx over dt. Alrighty. So I'm just going to use some algebraic manipulation so we can get to where we can just find the arc length directly by just having the set of parametric equations. So if I apply this square, that means I have the integral from a to b of the square root of, and notice how this keeps getting bigger. If I apply the square, that means I have this dy over dt squared over dx over dt squared plus 1. But what I'm going to attempt to do here is I actually want to get common denominators. So that plus 1 is going to have the denominator as this. So I'm going to have dx over dt squared over that, and I'm still going to have the plus. Great. Well, if you notice, and if you remember properties of roots, I can actually take the root of the numerator and the denominator separately. So the numerator, there's nothing I can do because of this plus sign. So it's still going to stay as dx over dt squared, and this is still going to stay as dy over dt squared. But the denominator, since it's by itself, the square root of dx over dt squared is just dx over dt, and I still have this dx. Technically we're done, but I'm just going to show you one algebraic manipulation because, I mean, if this is with respect to t, we can't have dx, we need dt. Well, remember that when you are dividing by a fraction, it's the same thing as multiplying by the reciprocal. So I still have this dx. The reciprocal of this is dt over dx. Cancels out, leaving us with the arc length from A to B is equal to the square root of dx over dt squared plus dy over dt squared dt. And that, ladies and gentlemen, is how you find arc length in parametric mode. Now, I decided not to do an example for this part because, as you can see, all of this is really old material that you already know how to do. It just looks a little differently now. And really, you know how to find the derivative of the parametric functions with respect to t. From there is just algebra. So make sure that you try the homework. Thank you for watching. If you have any doubts, please make sure that you give me a comment and I'll try to answer it for you. And I will see you guys next class. Thank you for watching.